Okay. So my hope is that a lot of this is going to be reviewed from last year. Did you guys look at rational functions last year? Did you look at vertical asymptotes, horizontal asymptotes? Remember, there were like certain conditions when it had a horizontal asymptote that was y equals 0, and sometimes it was you take your lead number divided by your lead number. Does that sound familiar to you? We're going to go over all this again today, but so good news, bad news. Bad news is there's a lot of moving parts when it comes to rational functions because it's basically two polynomials dividing each other, right? Good news is it all relates to stuff that we've already done. So this is all about finding the relationships. And we're just going to go through and draw those relationships, fill out a bunch of these boxes, and then we'll look at a couple examples together. So what do we see? When I look at this function right here, and here's the factored version of it, the x-intercepts come from the factors in my numerator. Those two factors right there are what gave me those x-intercepts at -1 and a 2. So roots in your numerator give you x-intercepts. All right, so we're going to fill out this box down here for roots of the numerator. I need to factor this thing. I can factor, I'm just focusing on the numerator. I'm not even going to bother with the denominator here. I could factor a GCF of 2 out. And I would have x squared minus x minus 2. And I think that factors even further. Yeah, it does. In fact, this is the same thing from down up here. So I'm just going to cheat it, copy that down. So we look at our factored version, we look at our two factors up here, set them equal to 0 and solve, and that's going to give us our x-intercepts. One of them's going to be at -1, 0, one's going to be at 2, 0. Those come from the numerator. Does this remind you a little bit of polynomials? Polynomials also had x-intercepts that were zeros or came from the factors. But we're dealing with rational functions, so it's only the factors of the numerator that give us x-intercepts now. So that's how we would get these two. That's where it's crossed. Factors of the denominator, and this should be familiar to us from chapter 1. Factors of the denominator give us vertical asymptotes. Those are going to be discontinuities, some places where some points that are, or some values that are not included in the domain of our function. So vertical asymptotes box down here, let's fill this one out too. If we were to factor on the bottom here, we would get x plus 4x minus 3. And please do me a favor, when you're writing vertical asymptotes, don't do like I did right here. I need you to give me equations. This would be x equals -4 and x equals 3 would be my vertical asymptotes. In fact, let's cross this out and write what this should be. That should say x equals -4 and x equals 3. Asymptotes are lines, and lines get equations. Remember, y-intercepts for any function is the same thing. You find f of 0. Basically plug 0 in for all of your x's. If we were to do this in this one, if we were to find f of 0, it would be 2 times 0 squared minus 2 times 0 minus 4 over 0 squared plus 0 minus 12. That's a whole bunch of zeros. Really what you got there is negative 4 over negative 12, which is positive 1/3. Which means my y-intercept would be 0, 1/3. So we find y-intercepts for rational functions the same way we find them for anything else. So it's 0 and for x. We doing all right so far? X-intercepts, y-intercepts, vertical asymptotes. Feeling good? Is this kind of coming back to you a little bit? All right, horizontal asymptotes. That all depends on what kind of rational function you're looking at. So there's a little bit of a shortcut to this. So this is a little bit of a mathematical shortcut. If you're interested, this kind of deals with limits, which we'll get into in calculus more next year. So I look at this and I look at the degree of your numerator and denominator. And if they match, if you have the same degree on the top and bottom, I'll sometimes refer to that as a balanced degree. Then you just take your lead coefficient over your lead coefficient. So I've got a 2 and a 1. My lead coefficients would be 2 over 1. So my horizontal asymptote would be y equals 2. Is this how you learned it last year? Yeah. Kind of, yes. Okay. Okay, great. So if it's balanced, you do your lead coefficient over your lead coefficient. If it's what I call bottom heavy, meaning your degree is higher on the bottom than it is on the top. So I got a first degree on the top, second degree on the bottom. Then you don't care what the coefficients are because it's automatically y equals 0. Did you guys deal with top heavy ones last year? So there is an asymptote if it's top heavy. So this will be a little bit different. So if the degree is higher on the top, then we're going to have to do division. We have to divide. So then the asymptote becomes y equals the quotient when you long divide. So the quotient after dividing. I'm just going to write dividing because sometimes we can get away with using synthetic division. We're going to do an example of this today. So if it is top heavy, you can divide this x squared into this thing. And if you do that, you take the quotient part. Okay, not the remainder piece, but the quotient part only, and that's going to be your asymptote. So it's possible for an asymptote to follow what's called an oblique line. So horizontal line, right? Vertical line, oblique lines at like an angle. Okay, but it's also possible for an asymptote to follow like a parabola. Sometimes your asymptote is the shape of a parabola, and sometimes it's the shape of a cubic. So we'll look at an example of it today. Doesn't come up that much. Okay. Holes. We get holes in our graph sometimes. What causes a hole in a graph is if you have a factor that matches in your numerator and denominator. So a lot of times people would see that and they think, "Ooh, that cancels out." Well, kind of, but there's going to be a hole in the graph because the original equation had this factor in the denominator, which means 2 would not be part of the domain for this function, right? Thinking back to chapter 1 stuff. So the graph can't go through 2. So you're not going to see a vertical asymptote there. You're not going to see an intercept there. Those two things cancel each other out and basically just create a blank spot in the graph. And what this looks like, if you flip your page over, this looks something like this when we graph it. Okay. So when we have a hole, we want to figure out what are the coordinates of that hole. So to find the x coordinate, you just take your factor, set it equal to 0, and solve just like we would if we were trying to find a 0 for it, right? So the x coordinate of my hole would be x equals 2. So my hole is at 2 comma. To find the y coordinate of your hole, you need to take that 2 that you just got, whatever that x value was, plug it into your reduced function. The reduced function is the function that does not include that x minus 2, that thing that you wanted to cancel at the beginning. So my reduced function would be x plus 3 times x plus 1 over x minus 4 times x plus 6. That would be my reduced function. I left all my x's out because I'm going to put 2 in for all those x's. And then you'd simplify that. And that will give you the y coordinate for your hole. What's that end up being? 5 times 3 on the top and negative 2 times 8 on the bottom. It's going to be negative 15 over 16. Almost negative 1. All right, so go back, recap. You're looking at an equation. How can you look at an equation and find your x-intercepts? Where do you look in your equation to find x-intercepts? Look at the top of the equation. Where do you look in the equation to find your vertical asymptotes? On the bottom of the equation. Where are we going to find our horizontal asymptotes or other asymptotes? We got to look at those lead coefficients. And hopefully either it's balanced, meaning the lead terms have the same degree, or it's bottom heavy. If it's top heavy, then you got to do division. We'll see an example of that in a moment. Yeah.
Okay, so for if it is top heavy, the quotient, you mean just like if we're to
Can I pause it and we'll come back to it? We're going to do an example of this later. Okay. So save your question, maybe jot it down, and we'll come back to it. Okay. All right. Let's flip over in the back and fill out the rest of these little boxes here, and then we'll do a couple examples here. So if we're going the opposite direction, if I've got a graph and I'm trying to find factors in the numerator, well, this comes from our x-intercepts. X-intercepts give us the factors in the numerator. And we know how to do that. We did that same thing with our polynomials. You remember that day we did the Desmos thing and you looked at the graph and you're like, oh, it has an x-intercept at 2. So x minus 2 must be a factor. Same idea here. Oh, wouldn't it be nice if this was just like polynomials? In polynomials, the powers determined your behavior at the x-intercept. Remember that? If it was an odd power, what happened at the x-intercept? Crossed over, right? If it was an even power, it bounced off. Same thing, but they come from the numerators now. So if you're looking at a graph and you see an x-intercept that's bouncing off of it, then you know you have an even power. If you're looking at a graph and you see an x-intercept where it's crossing through, then you know you have an odd power. All right, for our factors in the denominator, we've kind of talked about this, but this is the idea here is we're going backwards now. I've got a graph in front of me and I want to figure out what factors I have in my denominator. Where am I going to look on my graph to find factors in the denominator? We're going to look for asymptotes. What type? The horizontal or the vertical ones? Vertical asymptotes, control those. I don't know if you guys learned this last year or not. So the powers in the numerator tell you whether our x-intercepts bounce or cross, right? Did you guys learn about the asymptote dance last year? No, this will be a big hit at prom. Trust me, it is every year. So the powers in the denominator are going to tell you what the behavior of the graph looks like on your two sides of your asymptote. So if you think about my student, one of my students, prior students, made me this cute little chart. If you think about the asymptote as having two arms, right? If those arms are going in opposite directions, like these two things. So if it's dancing like this, that means you have an odd power. If the asymptote's two arms are both going the same direction, that means you've got an even power. So opposite directions versus same direction. All right. So when you're looking for asymptotes, you have to think about what's the asymptote dance that they're doing. So, and I find this easier to do sometimes if you got no cards. So can you look at this graph and tell that there's a vertical asymptote happening somewhere in here? This is the graph in the lower left of your page. Can you kind of look at that and see, ooh, there's a vertical asymptote happening in there. And look at what its arms are doing on the same on those two sides. Is this opposite or same direction? Opposite direction. One arm's going up, one arm's going down. So this is going to be an odd degree asymptote. Look at this one over here, odd or even. That's odd also. Okay. All right. How do we find A? Oh, wouldn't this be nice if it was the same way we found A for polynomials? It is. So basically we need to find a point on the graph, but not an x-intercept. You can try it with an x-intercept and see what happens sometime. It just won't work. And then we just substitute it into the function and solve for A. So same process that we did when we were trying to find A for a polynomial function. What if we're looking at a graph and we see a hole? Well, we're kind of working backwards from what we said before. If there's a hole, then that means I must have a matching factor in the numerator and denominator. You just need to figure out what that matching factor is. Anybody want to guess what it would be for this particular hole right here? What do you think? X minus 3 because the hole has an x coordinate of 3. So I want us to work a couple kind of basic problems from start to finish, and then we're going to go back and do a more detailed analysis of one or two rational functions. We'll make sure to hit one that's top heavy, so because it sounds like that's probably going to be the new thing for most people. So I actually want to start with the last example first. Let's see if we get this all in here. So we're going to start building our function. And I can see vertical asymptotes and x-intercepts. So I know I'm going to have some kind of rational function. And I'm anticipating that I'm probably going to have some a value out front. So I'll just go ahead and pop that in there for now. We'll come back and solve for it once we've built the rest of our functions. So let's look for factors that we're going to see on the top of our fraction. So we want to be looking, top of the fraction comes from what again? X-intercepts. I see an x-intercept here at 2. And look at the behavior. It's crossing the x-axis. You think that's going to be a single or a double? Probably a single, probably an exponent of 1. Possibly 3, but I'm thinking probably 1. So I'm going to assume that it's 1. So that would give me a factor of x minus 2. So x-intercept at 2 is giving me a factor of x minus 2. I'm going to draw myself some little arrows here. And I don't see any other x-intercepts. There is a hole, though. We'll come back to the hole. Let's deal with our asymptotes first. So I like, when I see a graph like this, I like to actually sketch in the asymptotes. So I can see that there's going to be an asymptote right here. That's x equals -1. It looks like there's going to be another one right here at x equals 3. So that leads me to believe that I'm going to end up with 2 factors in my denominator. So x equals -1 and x equals 3 should give me factors of x equals -1. That must be x plus 1. X equals 3, that would be x minus 3. And then our only other factors can come from holes. This hole here has an x coordinate of 6, it looks like 6 commas something. I don't really care too much about the something right now. The 6 is going to help me find that repeated factor, that one that's going to be in both the numerator and the denominator, which should be x minus 6. You doing all right? Pause here for a second. Look over all those pieces, all those factors that we've just created, and see if you have any questions. Do me a favor and double check our powers on all of our factors too. Do we need squares on either of these factors in the denominator? Let's look at these asymptotes again. I think we said a moment ago that they're both going to be odd because the arms are going opposite directions. Here and here. So they're both odd. So they're either to the first power or the third power. We'll assume first power. Yes.
So because the horizontal asymptote is at y is equal to 0, then can we assume that there's going to be more, that's going to be bottom heavy?
Oh, wait, good observation. Yeah, so you're noticing that our horizontal asymptote is y equals 0. We can kind of see that fitting in there. And if that's the case, then yes, we can assume it's going to be bottom heavy in terms of degree. So, is that looking bottom heavy? Yeah. So that's a good clue that this is not x minus 2 to the third power, right? We know it's not second power because we're not bouncing off it 2. But it could be third power, right? Could be an odd. But if we made it third power, then we would have a higher degree on the top, right? Third power here plus another one would be degree 4. We'd only have degree 3 on the bottom. We wouldn't be seeing a horizontal asymptote if that were the case. We'd see an oblique or a parabolic or cubic asymptote.
Oh,
so we know for sure that this isn't a higher degree. If I wanted to bump this up, then I'd have to bump these two up as well. We need to make it bottom heavy. It needs to be bottom heavy. So, but in general, for these, for rational functions, assume that your powers, your multiplicities are either going to be 1 or 2. Okay? Assume it's going to be 1 or 2. So the big thing we have left to do is find A. In order to do that, we need a point. We need to pick a point, and it can't be an x-intercept. You don't want to use a hole either. So what other point do we know for sure is on this graph? There is a y-intercept at 0, 2. So let's use our y-intercept. We'll use that 0 for x and the 2 for y. And rewrite our equation. So copy the format down here. And I'm just going to pop 0 in for all my x's and 2 in for my y. And then that should give us an equation we should be able to solve for A. Those cancel. That's just A times 2/3. So A must equal 2 divided by 2/3, or 2 times the reciprocal of 2/3, which is 3. So now finally we have everything we know to write this equation. F of x equals 3 times x minus 2 and an x minus 6 on the top, x plus 1, x minus 3, and then another x minus 6 on the bottom. All right. So please take a second and just look over all the pieces of that problem. Are you feeling confident about where we got all of these original factors from? Are you feeling confident about how we found A? Points substituted in x and y values. Some good questions on here. What questions can we help answer?
I don't think you factor it into like the 1 x squared minus ax plus 12 over whatever that is.
Oh, you want to multiply this out? We can. Yeah. So that would be like standard form for a rational function if we were to multiply all this stuff out. In general, I'm going to tell you, if they ask you to write an equation, unless they say specifically to put it in standard form, just leave it all factored. Good question. Other questions? All right, let's do this one up top. All right. So this time we're going the opposite direction. We're going to analyze this thing, figure out as much as we can about this, and then graph it. So in this format, there are a couple things that I can see in this format. This looks like a bottom heavy, doesn't it? In terms of degree, x to the third on the bottom, x to the first on the top. If it's bottom heavy, what's that say about our horizontal asymptote? So y equals 0 for horizontal asymptote. So I'm going to go ahead and sketch that in. Usually use dashed lines for my horizontal asymptotes and vertical asymptotes. The other thing that's convenient to see in this form is your y-intercept is usually easier to come up with in standard form. So to find our y-intercept, we'll do f of 0. And I think we're going to run into some trouble here, aren't we? If I plug 0, I'm going to get a -1 on the top and a 0 on the bottom. So what's that tell us? Where's our y-intercept? There isn't one. There is no y-intercept. This is undefined. So there is no y-intercept. This graph will not touch the y-axis. So we've already got a prediction as to why. Why do you think it won't touch the y-axis? What do you think is going to be right along the y-axis that's going to keep us from touching the y-axis? Vertical asymptote, right? Because the graph cannot cross a vertical asymptote. You know, graphs can cross a horizontal asymptote, though, right? We just saw an example of one that did at the bottom of the page. Graphs are totally allowed to cross a horizontal asymptote. Common misconception, but they can't cross a vertical asymptote. All right, this would be easier for us to talk about intercepts and asymptotes if we could factor it. The top doesn't really need any work. That's already factored. On the bottom, let's see, we can factor an x out of both of those. That would leave us with x squared minus 4. Ooh, x squared minus 4. That's difference of squares. Nice. So that factors a little bit further. Looks like we're going to have one x-intercept, agreed? At x minus 1 will give me an x-intercept of 1, 0. Let's go ahead and draw that in. It's right here. And at that point, are we going to be crossing the x-axis or touching the x-axis? Look at your power here. Power of 1, that's an odd power, so we should be crossing. And now we can use our factors in the numerator to come up with our vertical asymptotes. So we should end up with 3 vertical asymptotes. So x equals 2 and x equals -2. And what's the third one? That's not our idea of the x equals 0. Otherwise known as the y-intercept, which we kind of predicted. That's why we weren't going to have a y-intercept. I'm sorry, x equals 0 is the y-axis, which is why we didn't have a y-intercept. So let's sketch those then. So one of our vertical asymptotes is going to be right over the y-axis. One's a -2. And one's a +2. So my recommendation is when you do problems like this, and this is mostly what you'll be doing in this section, they'll give you the equation. You'll have to sketch the graph and analyze it. My recommendation is that you draw all the asymptotes and intercepts first before you graph it, and then pick up your graphing calculator. Don't just reach for your graphing calculator first thing. You want to do as much of this as you're on your own as you can. I used to really stress for my students being able to graph these by hand without a graphing calculator, and they're fairly simple to do that way, but you will have access to a graphing calculator. Okay, when I test you over this stuff, the whole test will have graphing calculator available. So I'm going to show you how you can graph this without a graphing calculator, how you can kind of use the clues that we have available to us to figure out what the shape of the graph is. But just know if you ever got stuck, this isn't that important. Punch it into your calculator. That's going to tell you sort of the shape of the graph in between these intercepts and asymptotes. So let me show you really quickly how we could do this. I know that my graph is going to be hugging. I know it's going to be hugging along my horizontal asymptotes at the far ends. And as I move away from the far end, what I don't know right now is, am I going to be swinging up here to meet this vertical asymptote, or am I going to swing down to meet that vertical asymptote? So to figure that out, what I would want to do is pick some number out here, substitute it in for X, and see if I end up with a positive or a negative. I don't really care what the value is. I just want to know if it's a positive or a negative. So I'm going to pick 10 because 10 is pretty easy to deal with. If I plug 10 in for X here, am I going to get a positive answer or a negative answer? I'm going to get 9 on the top, and that's going to end up being 1,000 minus 40. So 9 over 1,000 minus 40, it's going to be positive. So we're going to get 2 positive numbers. So I know that out here, my graph is going to be in the positive direction. Again, as it moves towards this vertical asymptote, it wants to either curve up like that or go down like this. Which one's it going to do? I'd say it's got to go up, but here's my reasoning. We know it's positive right here. If I swung down, wouldn't that cause me to cross the x-axis? We're allowed to do that, but I only have one x-intercept, and it is not over here. That's the problem, right? We can do that. We can cross the horizontal asymptote, but we can only cross the x-axis at places we know we have intercepts. There's only one place on this graph where we're going to cross the x-axis, and that's right here. So I can't swing down because that would cause me to cross the x-axis at a place where I don't have an x-intercept. So it's got to go up. All right, now we're thinking about that vertical asymptote here. I want you to focus your attention on it. And that came from this factor right here. What kind of dance should that vertical asymptote be doing? Should it be doing one of these things? Or should it be doing one of these things? So it's got to be going opposite directions, right? So I know that if it's going up over here, then it's got to be going down on this side of the asymptote. Does that make sense? Where it's got to be going down there? If it's up on one side, it's got to go down on the other side because this was multiplicity 1. Now, if that had been x minus 2 squared, I'd have it going up on both sides. But since it's just x minus 2 to the first power, odd multiplicities are going to go in opposite direction. So I know it's going down here. Okay. Now I'm going to need to rise up to meet this x-intercept. We know we're going to cross there. So I'll go ahead and cross over to my positive territory. Now, do you suppose I'm going to keep going up as I hit this asymptote, or am I going to do a U-turn and go back down? If I did a U-turn, I would have to cross the x-axis again to go down, wouldn't I? And I don't have an intercept there, so it's going to have to go up. All right, that asymptote was also a single, wasn't it? Single asymptotes go opposite directions, so if I'm going up on this side, I must be going down on this side. I'm down here, and it's going to rise up, and then I'm heading towards another asymptote. Again, either I got to swing up or I got to do a U-turn and go back down. What do you think this time? Got to do a U-turn, right? Because we can't cross. Can't cross there. There's no x-intercept. I don't know how far I come up, but eventually it is going to have to do a U-turn and go back down. All right, I'm on my last asymptote, which was also a single. If I'm going down on this side, I must be going up on the other side. And then the only other feature I need to make sure I hit is at some point it's going to have to come back and connect up to my horizontal asymptote. There's no more x-intercepts. So roughly that's what that graph's going to look like. I think it's a good idea to try and sketch it by hand before you drop it in your calculator, but if you're strapped for time, do this for me. Promise me you'll do at least this for me. Draw those asymptotes and intercepts first before you put it in your calculator. At least do that. And then if you have time, try and guess what it's going to look like by hand like we just did. But if you don't, just plug it in your calculator, and then your asymptotes and your intercepts will kind of give you almost a framework to draw the rest of it in there. You'll be able to see that, oh, we got a little U-shaped piece here, and there's a little S-shaped piece here, and some curvy things on the side. Okay. All right. So that's it for that piece of the notes. We're going to switch over into your notebook now and do a couple more. Any questions before we move on? Questions? All right, let's do this. All right, this a little bit. So we're going to analyze and graph. You guys are going to love this. We just analyzed in the last chapter. You guys remember what the book expected from us and what I expect from you when I say analyze? Oh, yeah. So pretty long list. Give me a couple things. This is 2.6, yes. This is 2.6. What do we got to do when we analyze? A whole bunch of things. Give me a few. And behavior, domain, range, horizontal asymptotes, vertical asymptotes, x-intercepts, y-intercepts, symmetry, odd, even, neither, bounded above, bounded below, not bounded. What else did we do? I put a whole list of it on Canvas. I'd like you to write this down in your notes, though. When it says analyze, see the example on page. Sorry. See example 6 on page 242 for expectations. What did I forget? Oh, local maxima, minima, increasing, decreasing, and behavior. And then we're also going to do behavior at the asymptotes. And this might be a little bit new for you guys too. All right, are we ready for this? It's going to be awesome. So we're looking at it in unfactored form. Let's go ahead and factor it. We're going to need it eventually. Again, my offer still stands from last chapter. If you need any help getting your factoring skills back, or potentially even building them up for a first time, please let me know. I'd be more than happy to sit down with you and practice, give you some tricks. At this point, though, my expectation is I give you something like this, you should be able to have that factored within 10 seconds or so. Well, yeah, we got to start somewhere. I guess domain, range. Let's wait on domain and range. Let's do those last. Range we got to do from the graph anyway. So how about intercepts? X-intercepts. Those are going to come from these factors in the numerator. In this case, our x-intercepts are going to be, remember, x-intercepts are points, so give them the proper respect that they deserve. They need x and y coordinates. It looks like 2, 0, and 1, 0 to me. It would be negative 1, 0. Thank you for that correction. Double check everything else here. Yeah, and cross or touch, cross or bounce for these two. They should be cross for both. Yeah, because they're both power of 1, which is odd, which means we're going to cross the x-axis. Those 2 points. I suppose while we're talking intercepts, we might as well do our y-intercepts. We'll just find f of 0. So if we put 0 in for all of our x's, and I'm thinking this version looks a little easier for me, everything would disappear except for the -2 in the numerator and the -3 in the denominator. So I'd say our y-intercept is going to happen at 2/3. But of course, it's a point, so let's give it the respect it deserves. 0, 2/3. Vertical asymptotes seems like a good next step. That's something that should come pretty easy. There's only one factor in the denominator, so we should only have one vertical asymptote. X equals 3. I'm going to write horizontal asymptote. This technically is not a horizontal asymptote. It's an n power asymptote, or n behavior asymptote is technically what it is, but whatever. They're not vertical asymptote. All right, here's the deal. Since we're top heavy on this one, we've got to do division. You got your choice, long division, synthetic division. On this one, we could definitely do synthetic division. You want to go ahead and do synthetic, or should we do a long division so you see what it looks like either way? What do you think? Let's do long division. Why not? Long division is fun. Last time we did long division, we were dealing with polynomials and factors of polynomials, and we expected we were going to get a remainder of 0. Can we keep that expectation right now or no? We cannot. Chances are we will not have a remainder of 0. So if you get something other than 0, don't let that shock and surprise you. It's going to be okay. So go through your steps for long division. I need to be careful with my signs. I've already made a couple sign errors today. 2x 2 times. Watch those. I want you to recall that when we do long division, oops, sorry, I'll give you a moment more. When we do long division, we are creating a new version of our function, a new representation, I should say. It's the same function, But we've created a different way we can write it. These are the same thing, we just factored. We just divided this, and we found that our quotient was x plus 2, and our remainder was 4, and we always put that 4 over top of the thing that we were dividing by. Do you guys remember back at the very beginning of the year when we were practicing long division, and I insisted that you write your final answer in this format? I said it's going to come up later on, and you're going to want it in this format. And it's going to happen again in Calc next year, but this is one place where we want it in this format. If I went in my graphing calculator and I graphed these 3 equations, they would all match. They're exactly the same thing. All right, so our horizontal asymptote, I should see our end behavior asymptote, because it is not horizontal, is y equals x plus 2. Y equals x plus 2. It is the quotient portion of this. This is my quotient. And that's where I get my end behavior asymptote from. So you can see sometimes if you do the division and if you had like x squared plus 2, now your end behavior asymptote becomes y equals x squared plus 2. It's going to be a parabola. Any questions up to this point? I'd like to go ahead and start building this graph, and then we'll come back and do the rest of our analysis in a second. So I've got to kind of scroll. I'm not going to be able to see all the pieces and parts, but I want to make a nice accurate graph. In your homework, when it asks you to graph, I want to see good, accurate graphs on graph paper with things in the right places. So let's put a couple of points on our graph where we know our x-intercepts are going to be. There's one at 2, 0, and one at -1, 0. Our y-intercept was at 0, 2/3, so we'll kind of eyeball that in there. Bless you. We had a single vertical asymptote at x equals 3, so draw me a vertical line at x equals 3. And then our end behavior asymptote was y equals x plus 2. Are you guys comfortable graphing y equals x plus 2? Do it as a dashed line. Right now, my Algebra 1 students will look at that and say, that has a slope of positive 1 over 1 and a y-intercept of 2. They're adorable. All right, so those are all the pieces. Now we're going to just graph something that fits into it. So here's the deal. When you have an asymptote that's not a horizontal asymptote, if your end behavior ends up being oblique like this one or ends up being quadratic or cubic, remember that only controls what the graph looks like way, way off to the left and way, way off to the right. Doesn't have any impact on the graph. I'm sorry, that's not true. There's very little impact on the graph in between. Okay. I know that way off to the left and way off to the right, my graph is going to end up so incredibly close to that line that they might as well be on top of each other. They won't exactly be on top of each other, but it's going to get closer and closer the further out it goes. So that just controls what's going on the outside of your graph. On the inside of your graph, you got to look at your vertical asymptotes and your intercepts. So I'm thinking I'm going to start from the left this time because I see these points that are kind of giving me an idea of the shape of the graph. right? I know that I have to sort of be really close to that diagonal line. And as I get close to this, I knew that I was going to have to cross here, which makes sense because I got to get up to this point and then back down to this point. And I'm going to cross at that intercept also. I've only got the one asymptote to worry about. When I head towards that asymptote, am I going to go down or am I going to turn around and go back up? Could I U-turn it and go back up here? No, there's no x-intercepts here, so it must be going down on this side of that vertical asymptote. And on the other side of the vertical asymptote, must be going the opposite direction because it was a power of 1, right? So I should have made a note up here with my vertical asymptotes that we're going opposite directions on the two sides of that. I just added in this little note here if you'd like to add that into yours as well, opposite directions because it was a power of 1, which means I got to be going up over here on this side of it. And then what's going to happen? Well, there's no intercepts or anything over here, so eventually it's going to have to curve around and head back towards that end behavior asymptote. So go with something like that. Okay, this next part might be new for a lot of you, so if you need a moment to wrap something up so you can give me your full attention, give me the universal sign. Anybody need a minute? We all got our graphs made? Do you have any questions about that graph before we do this new piece? I don't know if this is new for sure or not. We're going to use limit notation to describe the behavior of the graph around the vertical asymptotes. So we've used limit notation for end behavior before, but we're going to use it now to describe the behavior around this vertical asymptote. So let me give you the structure that I'm going to use first. And you guys can tell me if you've seen this before. So the limit as x approaches this vertical asymptote is happening at 3 from the left of f of x equals, and the limits as x approaches 3 from the right of f of x equals. Does this look at all familiar to you? Have you seen limits to a number from the left and from the right? So it almost looks like a little exponent on it. So if this is new to you, make yourself a little note that that means from the left. And this means from the right. So imagine yourself driving along your graph from the left, and you're heading towards this asymptote here. Which way are you going to turn? Up towards positive infinity or down towards negative infinity? Down, right? If I'm coming in from the left, I'm going to swing down to negative infinity. So this says driving along my graph towards 3 from the left. I'm going to be heading down towards negative infinity. Now this one says driving along my graph towards 3, but this time from the right. So I'm coming in from the right towards 3, and this time it looks like I'm heading up towards positive infinity. Do you see how that works? So when your book has instructions that say describe the behavior, it'll say use limit notation to describe the behavior around the asymptotes. That's what we're doing here. All right, so I'm gonna ask you guys to do a few things on your own. Could you go ahead and find me the end behavior and write that out with limit notation also. End behavior. Just like we did back in chapter 1. And when you're finished with that, see if you can find me some local maxes and local mins. I think there's one of each. Let's round off to 3 decimal places for these. And when you've got local max and local min, then you should be able to tell me about increasing and decreasing. Oh, that fun chapter 1 stuff. Don't forget your parentheses when you're typing this in your calculator. Hey, that's just like what we drew. Oh, I think that's probably 5. You think that's 5 for that local min? 5.00000001. When a computer tells you 5.00000001, we're gonna say that's a 5. Local min at 5. Huh. Well, that's nice and clean number. Well, we're just gonna get in under the wire today. The big thing that we didn't get to is domain and range. We could talk about boundedness. Is this bounded above or below? No, there's no boundedness here. Symmetry, nah, no symmetry. It's not odd or even. Once you've got that local max and that local min, though, you should be able to come up with domain and range. I'm going to add that onto mine as well. Let's put them right up here. Oh, did I tell you guys? I'm okay with this now for domain. If you want, if it's everything except for something, you can just write all real numbers except the things that it's not. I'm okay with that now. We've had enough practice with interval notation. I feel confident you guys got interval notation now. That's the reason I forced you to do it that way before. But if you want to just tell me it's all real numbers except for 3, that's fine. Going forward. Range. I think range. I'm going to want to use intervals for this. Negative infinity comes up to that local max of 1. And then picks up again at 9. It may help you with all the domain and range stuff to actually label your points, your local mins and maxes. Okay, so the homework assignments on Canvas, I put a little star there. I've made a list of all the stuff I want to see. You've got like 4 problems where it says analyze. So when I check on Friday, I want to see for those 4 problems that you've got all this stuff on there. All this stuff. Oh my gosh. So much. You can do it. I believe in you.
Can we check?
Yeah, give me just a second. Anybody have any questions? Okay.